Okay, in last class we have covered shunt generator under self-excited DC generators. In this lecture we will be covering the remaining three types of self-excited generators, that are series generator, compound generators, cumulative compound and differential compound generators. Now first let us take up DC series generators. Here in series generators, the field winding are connected in series with the armature circuit. So all series windings are connected and brought the terminals outside like this, and the armature terminals are brought like this, and they are now connected in series like this. This is no load. Okay, so here this circuit is RA and this is series field resistance RSE, and this is armature resistance, and IL in this series generator is same as armature current, and the governing equations will be IA is equals to IL is equals to IF. So all are same. IF is also the field, series field current is same as armature current, and load current is same as the field current, and the terminal voltage VT is now given by EA minus IA into RA plus RF resistances. So this is IA into RA plus RF resistance. Now if you constructionally, if you notice, the series field windings are slightly different from the shunt field windings, because series field windings will be carrying the same armature current. The IF is equals to armature current. The current is very large. Armature current is very large as compared to the shunt field current. So constructionally the series field will have less number of turns, armature resistance, as compared to the shunt field winding. Number of turns in shunt field is very large, and the resistance is also high, but field current is very small compared to the armature current, and here in this case field current is equals to armature resistance. Okay, for a given same amount of MMF to be generated in both cases. So for same amount of MMF or flux density under the pole shoes, so the series field winding will have less number of turns and more number of current as compared to the shunt field ampere turns. Now coming to the characteristics, OCC, as I said earlier, it is same for all the machines. We will be drawing the shunt series field windings, and we will be exciting it through a separate source, and we will find out the IF versus induced EMF. Okay, and we can draw the OCC characteristics. But when it comes to the terminal characteristics, VT versus IL, before loading the machine has to be started. It should be operating at no load conditions. Now when the machine is started rotating through the prime mover from 0 to rated speed, because now I am not connecting any load, there is no load, just it is mechanically rotating or increasing its speed from 0 speed to rated speed. Due to residual flux in the core, as the speed increases, the voltage at the terminals appear. If I place a DC voltmeter here at no load condition, so as it is rotated at rated speed, right? Now due to residual flux, there will be a small no load voltage appearing at the terminals, this point, right? So because armature current is not there, IL is not there, IF is field current is not, the field contribution is very less, or field because the current is not flowing through the series field, so the flux produced by the field current is not there. So only due to residual flux the voltage is developing. Now from this position, as the loading is now increasing, now I apply some load, slowly gradually I increase the loads. Now this increase in load current will have two effects. One is, with the increasing in load current, the field excitation increases and EA increases, and as EA increases the terminal voltage increases, the EA will try to increase the terminal voltage. But with the increasing load current, that is armature current, the armature drop will increase, and which try to cause the terminal voltage to decrease. So there are two effects with the increasing in load on the machine. One, try to increase the terminal voltage with the increasing load current. This is during initial loading conditions due to EA increase. And the other effect is, with the increasing in load current, the terminal voltage decreases. This is due to core saturation at higher loads, at high loads. Due to core saturation, this effect is now reduced, but this due to armature reaction and the voltage drop, this try to reduce the terminal voltage. So there are two forces acting on the machine simultaneously. Due to this, what is happening, the characteristics, terminal characteristics will initially try to raise as that of the OCC, and it slowly drops like this. This is only, if I take, this is only due to IA RA drop, and that's it, only due to IA RA drop, right? But if I also take the effect of armature reaction, then this would be little more severe, like this. This is due to IA RA drop as well as armature reaction. So the terminal voltage slowly increases from no load to a maximum value here somewhere, and then up to this the EA effect is more compared to the IA RA drop and armature reaction, and beyond this, the due to core saturation, the EA is not predominantly increased even for increase in IA, but the armature reaction increases and IA RA drop increases, and the net voltage, terminal voltage tries to come down, right? So this is how the terminal voltage looks like as compared to the shunt generators, where the characteristics are actually like this. The terminal voltage falls like this. Now here, depending upon the armature reaction effect and all that, so the voltage characteristics, terminal voltage characteristics will be drooping like this. Here in this case, the voltage regulation is a positive voltage regulation, where no load voltage is greater than the full load voltage, right? So that is why a positive regulation used to be there in the shunt generator. But in case of series generator, the no load voltage is very small, and the full load voltages, terminal voltage will increase. So this term is greater than this term, so we have a negative regulation, voltage regulation, in case of series generator, DC series generator. This is what you need to observe. Now series generators are used in special cases where the steep voltage characteristics can be exploited. So as shunt generators are widely used and compound generators are widely used, but series generators are specially they are used where this type of characteristics is more suitable, right? Now one such example is arc welding. So during arc welding, this negative slope, right, is more advantage, right? So this is what the arc welding requires, this sort of characteristics. So during arc, what happens when the contacts of two electrodes touches each other, the current increases and the voltage drops. Voltage drops and current increases, and the operating point will be somewhere here. But when the operator tries to separate the contacts, right? So what happens here? The arc try to persist. Current reduces with the increase in the voltage across these two terminals, okay, contacts of the electrode. So with the increase in the voltage, current reduces. So this is how this type of characteristics is more beneficial in case of arc welding. So that is where the series generators are employed, not everywhere. Now let us talk about the cumulative compound DC generators. Here we have both shunt and series field windings in the machine. Shunt field and series fields both exist in the machine, compound machine. And the MMFs due to these two windings aid each other. So the MMF components will be aiding each other. That is what I have shown here, the dot notation. The current is entering into the series field, as well as the current is also entering into this current IF is also entering this dot position in the shunt field winding. So both currents enter into dot notation, then their fields will be aiding each other, not opposing, they will be aiding each other. Okay, so in compound generator, cumulative compound generator, the shunt and series field MMFs will aid each other. We will talk about the differential compound DC generator next, but here in cumulative they aid each other. So the net MMF in the machine during the operation is given by F net is equals to the field MMF plus the series field MMF. This is shunt field MMF, series field MMF minus the armature reaction. Armature reaction is always subtracted. So this is NF into IF star. This is net equivalent ampere turns in terms of number of turns into current is equals to NF IF, and this is series field winding turns into armature current, because armature current is flowing in the series field winding, and armature reaction MMF. So this plus this minus this one. So the equivalent field current under any operating condition is now given by IF plus NSE by NF into IA minus the MMF due to armature reaction divided by the shunt field number of turns. Okay, this is the formula you need to remember. So the characteristics equations, the equations governing this circuit is IA is equals to load current plus the field current. This current plus this current is equals to the armature current, and the terminal voltage VT is equals to EA minus the drop taking place in the series field winding and armature resistance plus series field resistance into IA. So this is the drop, and IF is VT by RF. So these are the three governing equations of a cumulative compound generator. Now there are two connection types. One is long shunt and short shunt. Cumulative compound, we can have two connections. One is long shunt, which is what I have just shown. The shunt field is connected across the armature and the series field. Here it is connected. But in case of short shunt, the shunt field is now connected across the armature itself. The series field is now taken out. right? There is a small difference. The shunt field is now connected only across the armature here in case of short shunt, and long shunt, the shunt field is connected shunt to both armature and the series field winding. Okay, so here I have shown the circuit diagram for short shunt. This is shunt field current, this is armature resistance, this is armature, and this is series field winding taken out from this. So under this condition, IA is still equals to load current plus IF. This IA is still equals to the field current plus IL, but VT is now equals to, I say this junction voltage EA prime, so which is now VT is equals to EA prime minus the series drop, series field voltage drop, that is IL into RSC, and whereas EA dash is equals to EA minus the armature resistance drop, this drop, EA minus, this is EA minus this drop, right? And what is IF? IF is EA dash by RF. So these equations govern the short shunt cumulative compound DC generator. Now let us talk about the terminal characteristics VT versus IL, and the governing equation is VT is equals to EA minus IA RA into RSC drop. So this is I am talking about for long shunt. Now there are two effects in compound generator. There are two effects in compound generator with the increasing in load current, right? So one is with the increasing in load current IA, the IA into RA plus RSC drop increases, which causes VT to reduce, and the other one is with the increasing in IA, that is load current and hence IA, the series field MMF, which is NSC into IA, is increasing because of IA increasing, and this in turn increases the Fnet. Fnet is actually F plus FSC minus armature reaction. This is FF, shunt field, series field minus armature reaction. Because this is raising, the overall Fnet also increases. So due to this Fnet, the flux increases in the system, and then induced EMF increases, which in turn increases the terminal voltage. So there are two effects due to increasing in armature current. One is to reduce the terminal voltage, other one is to increase the terminal voltage. So they are simultaneously acting each other but opposing each other. Now these two effects oppose each other. Which effect predominates in a given condition, given machine? It all depends on just how many series turns were placed. So which one will predominate is actually dependent on the number of turns used for series field winding. So I can now use a series field with fewer number of turns, moderate number of turns, or more number of series turns. Now in case of few number of turns, then the machine, the compound generator is called under compound generator, cumulative under compound generator. If it is moderate, then it is a level compound generator. If it is more series turns, then over compound series generator. So what actually happens here is, so this is the first characteristics is the shunt generator characteristics. Okay, so due to the series field winding placed in addition to the shunt field, it is actually increasing the strength of the overall MMF in the machine. That is why the characteristics raises. So this is under compound characteristics, and this is level compound characteristics, where initially the raise is more than the no load voltage, and slowly due to saturation the drop effect increases, and then slowly terminal voltage falls. But at full load condition, again we will be adjusting such that the rated terminal voltage is exactly equals to the no load terminal voltage, and that is why it is called a level compound DC generator. And in case of over compound, where more number of series turns are used, the effect of increasing in MMF due to series field winding is more phenomenon than compared to the drop as well as armature reaction. That is why the terminal voltage raises and slowly it falls. But when it comes to rated terminal voltage, rated load, even then at this condition the terminal voltage is higher than the no load voltage. That is why it is called as over compound. And in case of under compound, the rated terminal voltage is actually lower than the no load voltage. So these three are the three types of compound generators based on the number of turns used or employed for a series field winding. Now let us talk about the graphical analysis. So the voltage control again, it is similar. It can be controlled by change in speed, or it can be controlled by change in field current. So as I said, the speed variation is restricted due to some constraint on prime mover. So this method is not used, and only method is the change in field current by changing the the supplied voltage to the field, or by placing some additional resistance in series with the field circuit. Now coming to the graphical analysis to determine the terminal voltage in case of a cumulative compound generator. So here the F net, MMF F net is equals to the shunt MMF, series MMF minus the armature reaction MMFs. So these two are acting opposite to each other. I say the equivalent effect on the overall shunt MMF is given by IEQ is equals to series field MMF, that is NSE into IA divided by NF minus the armature MMF divided by the NF. NF is the shunt field winding number of turns. Okay, so this is IEQ. Now this IEQ is added or subtracted to the main field current to get a resultant equivalent field current, right? So this is plus when IEQ is positive. When IEQ is positive, when this series field MMF is more as compared to the armature reaction, and IEQ is negative, means this is more as compared to this level. So depending upon the sign of IEQ, the overall equivalent field current will be either subtracted or added to the existing field current. Okay. Now, so I have drawn the magnetization curve and the field circuit resistance line, right? This is IF, EA versus ET. So EA graph I have shown and VT graph I have shown, right? Now this is IL versus VT, the actual terminal characteristics, IL versus VT. For a given speed of constant operation, for any field current, the induced voltage is always lies on this curve, the OCC curve, right? This EA always lies on this OCC graph with change in field current at constant omega. And when it comes to the terminal voltage of the machine, the terminal voltage, this voltage of the machine always lie on this graph for any field current given a particular constant RF. So that is why called a constant RF line. Now the governing equation say that EA minus VT, the difference between these two voltages, is equals to the drop, that is IA into RA plus RSC. This drop, this is always, this difference is always equals to this drop. So at every moment the vertical difference between the two graphs is always equals to the IA RA plus RSC drop for a given field current. Now I just wanted to calculate this drop to identify my terminal voltage. How do I do that? So when I given load condition IL, I calculate this drop. So I treat IA and IL are almost same. So I calculate this IA into RA plus RSC drop, and I draw a equivalent length of to scale this voltage drop IRA to scale. And if the machine is having some armature reaction and this effect, I equivalent effect, I calculate this one. Okay, so if it is positive, then I add like this, that equivalent, I equivalent. If it is negative, then I add opposite direction, minus I equivalent. So based on that, I can draw these two triangles. If it is I equivalent is positive, then IR drop plus I equivalent current, then this triangle is obtained. If I equivalent is negative, then I will be adding this vectorially IR drop and I equivalent current, then I'll join this. This is the two triangles based on the current, equivalent current is positive or negative. It can be either one for a given condition. Okay, so now what I do, I just bring this triangle and place such that this triangle touches both the VT line and EA line. It touches here at this point and this point on the OCC and RF line. Okay, so once I know this, then I can calculate the terminal voltage is this value. So this is no load. No load is the EA line crossing the VT line. This is no load. This is no load point, right? So for any other loads, now I can calculate this triangle, place on this, and then find out the corresponding terminal voltage. Okay, so in case of cumulative compound, because the voltage, terminal voltage rises, right? Because this is due to this triangle is fixing somewhere here above the no load condition. The triangle fits above the no load operating condition. That is why the corresponding terminal voltage will go above the no load voltage. But as loading further increases, the armature reaction effect and the drop effect reduces. Then the triangle now under that condition the IAQ becomes negative. So this is the equivalent triangle. Now this has to be fit like this. So under this condition the equivalent terminal voltage will come down like this. Okay, it will come down. So this is how the terminal voltage looks like, and I can calculate by placing the triangle touching the OCC graph and the RF line. Now let us talk about the differential compound DC generators. It is physically same, that is we have two series and shunt field windings, but only the difference is the series field winding MMF now opposes the shunt main field MMF. So I have shown here the dot convention. This is dot here and this is dot here. So in field winding the dot is entering, and in series field winding the current is actually leaving the dot convention. Okay, so that is why I say the MMFs are opposing each other. Constructionally both are same. So now the net MMF in the machine is equals to the shunt field MMF minus series field MMF and armature reaction MMF. So IF star is equals to IF minus NSE by NF into IA minus the armature reaction MMF by NF. This is what the equivalent net excitation current. The equations which governing this circuit is IA is again equals to IL plus IF. This armature current is equals to the load current plus the field current. But ET is EA minus IA into RA plus RSC, similar to that of the cumulative compound generator. Now again we have two possible connections, long shunt and short shunt also in differential compound generator. So short shunt will be connecting the field circuit, shunt field circuit across the armature like this. Again these will be the equations governing the shunt field. So IA is equals to IL plus RA IR, and VT is equals to EA prime minus IL into RA, and EA prime is equals to EA minus IA RA, and IF is now EA prime by RF. EA prime by RF. Okay, now only we are now talking about only long shunt. Now the terminal voltage characteristics, again in case of differential compound there are two effects, but now these two effects are having similar effect. Unlike in cumulative compound, they are opposing each other. Initially one is aiding and other one is opposing, but later the first one will be now opposing and second one will be the aiding. But in differential compound both will be having similar effect, and this is opposing in nature, that is it reducing the terminal voltage for increasing in armature current. So I say with the increasing in armature current the drop is increasing, and which actually reduces the terminal voltage. And the other one, due to series field winding, the increasing in current, the series field MMF increases, but which is actually opposite in nature to the main field, shunt field, so that net field will now reduce, and this net field MMF reduces the induced EMF, which in turn reduces the terminal voltage, because VT is equals to EA minus IL into RSC plus long shunt, right, RSC plus RA, right. This is what the governing is. So with the EA decreasing, VT also decreases. So two effects, but both are reducing the VT in differential compound generators. Now graphical analysis. So here the equivalent current is always subtracted from the net field current. So IF star is equals to IF minus IEQ. Okay, I have shown here. So the net field MMF, this is shunt field minus series field minus armature MMF, and IF is equals to IF star is equals to IF minus IEQ, where IEQ is the sum of both series field MMF and equivalent current plus the armature reaction equivalent current. Okay, so once I calculate the IARA drop and add vectorially this equivalent current IEQ, then I'll have a triangle. So I will be placing this triangle touching the 2 grams OCC and the RF line. Then I can calculate the corresponding voltages onto the terminal characteristics VT versus IL for a corresponding load currents. Okay, as the load current increases, the terminal voltage falls. Now in this case, differential compound, this is the shunt generator characteristics, where in cumulative compound we had all the characteristics either above the shunt field characteristics, but in case of differential compound characteristics, this is lower than the shunt generator. Okay, so this is lower than the shunt generator. So we have a varied set of the terminal voltage characteristics we can use. From the lowest V is differential compound, then comes the shunt, then comes the under excited cumulative compound, level compound, and over compound cumulative compound DC generator. Okay, so this is all about the 3 self-excited generators: series, cumulative compound, and differential compound generators, and their terminal characteristics to be calculated using graphical analysis. So I'll stop here. I hope you have understood.